Every AI agent you have ever used breaks eventually. You give it a long task. Around the 2-hour mark, it starts looping. By hour 4, it is editing the same file 3 different ways. By hour 6, it has forgotten what you originally asked for. This is not a quirk of one model. It is what happens when one stream of thinking has to carry an entire job by itself. And then on April 20th, 2026, Moonshot released an open model called K2.6. They pointed it at an open-source financial trading engine and gave it one instruction: make it faster. According to Moonshot's report, the model ran on it for a 13-hour stretch. 12 different optimization strategies, over 1,000 tool calls, more than 4,000 lines of code modified. When it finished, throughput on the most affected metric had jumped to nearly triple what it started at. The trick is not that K2.6 is smarter than every other model. The trick is that for those 13 hours, it was not one model. It was up to 300 copies of itself, working in parallel, coordinated by one orchestrator in charge of the whole thing. This pattern is called an agent swarm, and it is changing how serious AI work gets done. So why does a single agent break in the first place? 3 reasons. And these are not bugs in any specific model. They are architectural problems. You cannot fix them with more training data or a smarter base model. The first problem is drift. As an agent works, every action it takes and every result it observes gets appended to its context window. By step 500, the original instructions are buried under tens of thousands of tokens of tool outputs and intermediate state. Attention spreads thin. The model loses track of what it was even trying to do. The second problem is confident loops. One wrong assumption early in the run becomes the foundation for every following step. The agent tries the same broken approach over and over with slight variations, fully convinced it is making progress. There is no sibling thread to disagree with the bad assumption. No second opinion. The error just compounds. The third problem is no parallelism. A real engineering job has independent branches. Read the test logs. Check 3 different config files. Run the build. Investigate the database schema. A single agent has to walk these one at a time. That is hours of wall clock time spent on work that could happen all at once. What if you do not try to make one agent better at long tasks? What if instead, one model runs as many copies of itself as the work needs, with one copy in charge of the rest? That is the swarm. One orchestrator at the top, many workers below. The orchestrator gets the task, but it does not try to do the work itself. It decomposes. Each worker is a fresh instance of the same model. It gets one small bounded piece of work. Read these 3 files and report what they do. Run this test and tell me what failed. The worker starts with an empty context window. It does not see what its siblings are doing. It does its narrow job and reports back. Then it goes away. And now, look at what happens to those failure modes. Drift cannot accumulate, because each worker only lives for one short task before being thrown away. Confident loops cannot spread, because no single worker is in charge of the long-term plan. And serial bottlenecks disappear, because parallel branches are exactly what the swarm is built to do. The orchestrator handles disagreement. When 10 workers come back with 10 different findings, the orchestrator decides what to trust, what to throw out, and what to investigate further. It is the only piece holding the high-level plan. The workers are short-lived hands. The orchestrator is the long-lived mind. Which raises the obvious question: how does an orchestrator learn to be good at this? Here's where it gets interesting. Because the obvious answer, train the whole thing end-to-end, turns out to be wrong. The Kimi team tried it. The problem is credit assignment. When a swarm finishes a task and gets a reward, you do not know which subagent contributed and which one wasted compute. A correct final answer does not mean every worker did good work. A failed answer does not mean every worker did bad work. The reward signal is noisy and sparse. Training all the workers from that signal turns out to be unstable. So they did something different. They froze the workers. The workers are copies of the model snapshotted partway through training, locked at a fixed checkpoint. They never get updated again. Only the orchestrator gets reinforcement learning. The team calls this approach parallel agent reinforcement learning. The orchestrator gets a 3-part reward. The first part is the actual task outcome. Did the swarm solve the problem? The second part is the parallel reward, which fights what the team calls serial collapse. Without it, The orchestrator finds a local minimum where it just spawns one worker at a time and behaves like a single agent. The third part is the finish reward, which prevents the opposite failure. Without it, the orchestrator cheats by spawning a flood of pointless subagents to game any parallelism metric. The auxiliary rewards get annealed to 0 over training. Once the orchestrator learns when to parallelize and when not to, it operates on the actual task reward alone. The published result on K2.5 was up to 4.5 times faster than a single agent baseline on wide search tasks. That is the model where this mechanism was first introduced. K2.6 scales the same mechanism to 300 concurrent workers and 4,000 coordinated steps. Now there is one obvious objection. 300 copies of a 1 trillion parameter model is, on its face, absurdly expensive. How does anyone afford to run that? The answer comes from the model architecture. K2.6 inherits the same mixture of experts' design as the rest of the Kimi K2 family. More than 1 trillion total parameters, but for any single token of generation, only about 32 billion of those parameters actually fire. The model is divided into 384 expert subnetworks. Each token routes to just 8 of them. So the per token compute cost is roughly 3% of what a dense 1 trillion parameter model would cost. Multiply that by 300 parallel workers, and the swarm is still cheaper to run than a single dense frontier model would be on the same task. This is what makes the swarm pattern economically tractable. The mixture of experts substrate is what turns the math from absurd into reasonable, and this is part of why open weight models matter for the swarm pattern. Closed API providers charge a flat rate per token, no matter how the model runs internally. 300 parallel calls means 300 times that bill. With open weights running on your own hardware, you pay the actual compute cost, which scales with what the model actually does. So what was actually happening for those 13 hours on the trading engine? Now you can see it. The orchestrator was not coding. It was watching. The orchestrator broke the task into branches. One branch profiles the existing code to find hot paths. Another branch researches what fast trading engines look like. A third branch generates candidate optimizations. A fourth runs the test suite to make sure nothing breaks. Each of these is its own short-lived worker. None of them lasts more than a few minutes. None of them sees the others directly. They all report back to the orchestrator, which decides what worked and what to try next. 12 different optimization strategies got tried over the 13-hour run. The throughput numbers, moonshot reports are striking. One throughput metric jumped 185%. Another more than doubled. All of it inside a single 13-hour stretch. The weights are open. The mechanism is published. Anyone can run this. And every other lab is going to ship their own version of this pattern soon. If you want to feel where AI is actually heading, watch this. Not how big the next model is. How many copies of it can talk to each other at once.